Okay, and if you have a flame there, it's not so far off because the reactions are very, very fast. The chemistry is very fast. Even though it's many-step, but each step is like a nanosecond time scale, and so it doesn't take very many nanoseconds to burn up all your fuel. You have to worry about NOx formation in these kind of flames because it's very hot, and so it's so hot that the oxygen atoms that you make in the flame can attack the nitrogen to make NO plus nitrogen atoms, and then those nitrogen atoms will react further to make another NO. But in these systems, there's relatively little chemistry other than the NOx happening on the air side. But on the fuel side, there's a ton of chemistry happening in these systems because the heat typically conducts at least as fast as the molecules can diffuse. So the heat from the flame is conducting into the fuel side, and it's making the fuel very hot as it gets close to the flame. And it's so hot that a lot of chemistry can happen among the fuel. So the fuel itself is doing a ton of chemistry before it even mixes with the air. And so we call that pyrolysis chemistry. It's when you cook something in the absence of oxygen. So how do we model the pyrolysis? A very important thing about this is to realize that what's burning in a diffusion flame is not the fuel. It's the fuel breakdown products. So let me draw a little picture. Okay, so here's our flame, dotted line. Over here is air. In here, there's hot air. Okay? Over here is fuel. But you don't get to hot fuel because the fuel reacts as it gets hot. So here you have fuel breakdown products. And by the time you get to the flame front, you have small molecules. The fuel keeps breaking down. And what's actually getting to the oxygen at the flame front is small molecules. So if you're trying to compute this correctly, you really have to worry about this. So one thing is that the diffusion rates of the small molecules are larger than they are for the big molecules. So your diffusion calculation is kind of be screwed up by the fact this chemistry is happening. And also what happens is some of these small molecules are things like acetylene, C2H2, and they could actually polymerize and make things like benzene and polycyclic aromatics and maybe even soot. And so that's what you'll see in a diffusion flame a lot of times is you'll actually see soot formed on the fuel side. And that can be really bad because you can have particulate emissions from that. So you ever like a birthday candle, depending on exactly how long the wick is, sometimes you'll get a condition where you'll start forming soot on the flame side, which is on the, I guess, the inside of the flame, of the candle flame. And then in an unfortunate situation, some of those soot particles will actually escape and come up, and you'll actually, if you leave the candle lit a long time, you'll get a black spot on your ceiling because the soot particles float up and hit the ceiling. Right? How many of you guys have seen this? Yeah. And this is the reason why the candle flame is yellow, is the soot particles are radiating. So you've reacted the wax. What actually happened was the wax molecules broke down into small molecules, and then the small molecules formed acetylene, and the acetylene polymerized back up and formed all the way up to soot. All that happened before the hydrocarbon got to the flame front. In a very thin zone near the flame front, in that diffusion zone, the chemistry is happening so fast that the fuel can completely break down and get all the way to soot before the stuff gets to the flame front. So if we want to understand this, we really have to think about the pyrolysis chemistry. Now, you might be tempted to try to write down this chemistry. Is this going to work this time? Okay. Fuel molecules plus heat goes to smaller molecules. You might be tempted to write it with just writing some kind of omega for fuel and say it's some kind of Arrhenius form times the concentration of fuel. And maybe some of you have actually done this. This is like single-step chemistry kind of model. And you might actually be able to fit some limited data on the fuel decomposition of flames to this form. But if you did it and looked at it carefully, you'd find out that the fitted EA value is considerably smaller than the energy required to break any of the bonds in the fuel. So the EA for this process is much lower than the actual energy it takes to break any bond. So that's kind of weird. How can you have a reaction where the process is breaking a bond, but the EA is much smaller than breaking a bond? That's very strange. And also, you'd find that the concentration dependence is not really first order in fuel either. So if you ran it like different pressures, so you had different concentrations of fuel, you'd find that actually this formula does not really fit. But if you did it over a small range of fuels, a small range of temperatures, maybe you'd be able to fit it this way. Okay? But it wouldn't be, but it's not physical. Like the EA is too small to be physical. The A factor has like no relation to anything. And even the concentration dependence is not really right. So something is going on that's different than that. And what's happening is that the fuel pyrolysis is a multi-reaction process. So the way it works is that a radical, say, for example, an H atom, attacks the fuel, rips an H off of the fuel, and makes a fuel radical, R dot. And then the R dots at high temperatures, beta fission. Beta fission means break up, spit out an alkene in a smaller radical. And those reactions are really fast at high temperature. And so, for example, if you make a propyl radical, it breaks up to make a methyl radical plus ethylene, for example. And there's many, many reactions of this type where you're breaking a CC bond that's beta. So this is the alpha CC bond. This is the beta one. It's beta to the radical. So it's like 2 carbons away from the radical. You break that CC bond. And this left part, the right-hand part, becomes the double bond. And that's the alkene. And this part over here becomes a new radical. And this process keeps going until the R dot is so small that it can't beta scission anymore. So either the R dot goes all the way down to H atoms, or the R dot gets all the way down to methyl, typically. Okay. And then these R dots, whatever one you make, H atoms or methyl, they attack the fuel, and they make a new big R dot, and the thing goes over and over again. So this is what's called a chain reaction. A radical attacks the fuel, it makes the new radical, a radical attacks the fuel, makes a new radical, a radical attacks the fuel, makes a new radical, over and over and over, a continuous chain. And it might happen 100 or 1,000 times before anything else happens. So that's like the main process, is this radical chain. There are some other reactions that radicals can do, but this is, you're in the presence of a lot of fuel in a diffusion flame, because that's all you have on the one side is fuel, right? So when you make a radical, it's looking around to what to react with. The only thing it can react with is either by itself or it's going to react with the fuel, right? So by itself, it'll do that the fastest, it'll fall apart, but it gets down to a radical that can't fall apart, like these guys, and then it'll attack the fuel. And what happens pretty quickly, actually, you make these alkenes as the co-products, and they can either be attacked by radicals and do similar chemistry to the RH, or they can just fragment spontaneously because the CC bond strengths in alkenes are lower than the CC bond strengths in saturated molecules. And so at some point, you make enough double bonds, you'll make the CC bonds weak enough that at your temperature, they'll just spontaneously break apart, make more radicals. Pretty quickly, what's going to happen is that all the large molecules are gone. And all you're left with is a mixture of small alkenes, hydrogen, CH4, and a bunch of radicals. And this process is actually commercial. In the chemical industry, it's how we make monomers to make plastic. So ethene, like this one, ethylene, and propylene, this is the way they're manufactured. And so this process is run in like millions of tons a day around the world, lots of big giant units where they just take hydrocarbon, run into a hot pipe, and for about 1 second, and out the back end, they get a ton of ethylene and then some other alkenes as well. And then they separate those guys, and they send the ethylene to make plastic bags, and they send the propylene to go make insulation and wires and all the different stuff. And some of them, they make the fiber that's in your seat that you're sitting on. Yep.
Do they block oxygen?
Yeah, no oxygen, no oxygen. So it's just, they have just a heat full of the fuel, and they just provide the heat from outside. The whole thing is in a pipe. Inside's the fuel, outside is a furnace, and they just make the pipe super hot. The wall of the pipe is very, very hot, and that provides the heat to drive this process. This process actually overall is endothermic. It's being driven at high temperature by the entropy increase, because you're going from 1 particle to 2 particles.
I think a temperature more than 1500 K, yeah?
No, this one's usually about 1100 K. And it's limited by the fact that the metal of the pipes becomes unsafe if you go too high.
Oil for the cracking, right?
So,
oil to the petroleum.
yeah, they use oil. Or in the United States, they would use ethane and propane from the natural gas. But in Europe and China, I think they use oil and as the fuel. It doesn't matter. Whatever fuel you put in there, all the fuels do this. Actually, that's another interesting thing. So all the fuels are different when they come into the diffusion flame. Whatever fuel you put in there is what you have. But by the time you get to the flame front, they're all ethylene, methane, hydrogen, propylene. That's it. And it doesn't matter what fuel you started with. You make the same stuff. And so at the refineries, they basically get whatever hydrocarbon they got extra of. They put it into the pipe, and they cook it and make up ethylene to sell to the plastics plant to make the polyethylene. And that's the biggest chemical process. So in the chemical industry, this is a big news, and they spend a lot of time on this process. And they would like to run a higher temperature, and they're 100% limited by safety, that if the pipe gets too hot and it fails, then you have a major problem, because you have a very big pipe full of a lot of fuel that you're shining into a furnace at 1100 Kelvin, and then suddenly if the pipe opens, then anybody who's like within a mile of the place is likely to be dead, because you get a really big fireball. And this actually kills maybe about 10 people per year around the world when one of these pipes breaks. So they're very concerned about the safety of trying to keep the pipe not too hot. But its problem, they're relying in this case, actually interesting. They have the pipe is in a furnace. The furnace is much above 1100 Kelvin. It needs to be hot in order to have enough heat flux to the pipe. So the furnace is like 1600 Kelvin or something. The pipe is only 1100 Kelvin. It's being cooled by this endothermic reaction. So the endothermic reaction is keeping it safe. But if anything happens, like to disrupt the flow of the fuel, say there's some upset and the fuel doesn't come in fast enough, then there's not enough fuel there to do the endothermic reaction fast enough to absorb all that heat. And then the pipe wall temperature will go up. And it gets up to the failure temperature of the pipe, and then everybody's dead who's nearby. So this is an intrinsically dangerous process, not intrinsically safe. All right. So if somebody can think of a smarter way to do this, probably somebody pay you a lot of money to figure out a smarter way to do this. But so far, nobody figures it out. So that's what we do. All right. Anyway, this is happening also in the flame. In the flame, it's a little bit safer because you don't have a big pipe full of all the fuel. You just squirt a little bit of the fuel in through your fuel injector or something. And so you have a relatively small amount of fuel present, and you expect it to all burn up. So you make the whole thing so you can handle the total heat load from the thing burning up. All right, the rate for this reaction, why is it doing this? There we go. So at 1000 Kelvin, around there, it's about 1 second. That's how they run the commercial units. But if you're running a flame, your temperature is much higher. So by the time you get up to like 1400 Kelvin, as the fuel is approaching the flame front, the flame might be at 2000 Kelvin. When you're up to about 1400 Kelvin, by then the fuel is going to be completely destroyed in like sub-millisecond by these reactions. And the rate of this process is going to be the concentration of radicals, steady state, times concentration of fuel, because the rate limiting step is this attack of the radical in the fuel. And the steady state radical concentration is set by a balance between the slow bond scission of the non-radicals and the slow recombination of the radicals. So there's two different, if you want to calculate the rates here, you have to consider two different things. One thing is about what is making radicals, what is destroying radicals. That's going to control the radical steady state. The second thing is, once I have radicals, how fast do they react with the fuel? So that's sort of the propagation step of the chain. And you need to know them both. Typically, this thing is proportional to the fuel to the 1/2 power. So overall dependence is really actually 3/2 power of fuel, most commonly. All right, so why are the radicals so important? I have a whole lot of stable molecules, all these fuels and alkenes there, and we have a tiny bit of radicals, but somehow the radicals are doing everything. And my rate's just proportional to how much radicals I have. So why are they so important? It all has to go back to this Pauli exclusion principle we talked about. The Pauli exclusion principle does not allow two electron pairs to exist in the same spatial region. They just cannot be there. By quantum mechanics, they're smart. They just dodge each other. They're not going to be in the same spot. And the consequence of this is that molecules that have fully occupied valence shells, which is most of the stable molecules you know, repel each other. You try to bring them together, they always repel. And so you have like a van der Waals repulsion term, right? You know, the art of the 12th or something, some really strong repulsion. You just can't get them too close to each other because the electron pairs cannot both be in the same location. So you can't make the electron clouds overlap each other. The electronic structure is not flexible, so the electrons can't move out of the way. So if I try to jam Here's one molecule. Here's an atom. Here's an atom. It has this cloud of electrons around it. This has a cloud of electrons around it. If I try to jam these together, you'd say, well, why don't these electrons just move away? If they can't be in the same spot, let these electrons just move away so I can get the thing closer together. Here, like this. Why can't I just get to this situation? You think, right? So you start with them like this, and I squish them together. I should just mush the electrons out of the way. And the problem is for a closed shell molecule that these locations for the electrons are not really accessible. They're at a much higher energy than the valence shell. And it takes a huge amount of energy to move those electrons from the valence orbitals to this other location. And so for a closed shell molecule, there's nowhere to put the electrons. You try to bump them into each other, they can't do anything. You can't rearrange them in any way to try to make bonds or break bonds or do anything because the electrons have basically filled all the spaces there is. They're all in, all the stable orbitals are full. It's all closed shell. There's nothing, no action can happen. In contrast, if you have a free radical, it means you have a vacancy. You have like a hole, a space in your valence shell that's not occupied by anybody. And so it's just like a free slot. Do you guys know the game where you have like numbers and you're trying to slide the little tiles around to put the numbers in order? And there's like one empty slot and you slide it over. How many of you have done this game? You know what I'm talking about? Yeah. So it's the same thing here with the electrons. Because I have that empty hole, there's a space that an electron can go into. And then that gives me flexibility to move the electrons around inside the valence shell. And they can get to some different configuration that's more, breaks a different bond than the original one. So I can get to a different chemical structure. And so that's why the radicals are much, much more reactive than the stable molecules. Typically, actually, what you have is if you have a radical and a radical reaction, very often the reaction barrier is actually 0. The odd electron and the hole can just recombine with 0 barrier. So that's about as fast as you can get, right? And the radical stable reactions, they have some barrier because you do have to move the electrons around to a slightly less favorable configuration, but it's all inside the valence shell. And so the barriers aren't that high. So it doesn't take that much energy to move them. But the stable plus stable reactions, they basically don't happen, or the barriers are so high you don't see it very much. So the combination of the small barrier plus the high concentration of the stable molecules means that the radical plus stable reactions are much, much faster, usually typically 2 orders of magnitude faster than the radical plus radical or stable plus stable reactions. Okay, a very important concept is the concept of sealing temperature. So if I have a molecule, there's some temperature where it wants to just decompose. And so I have semi-radical. For this process to go, I have to have the radical break into an alkene plus R dot. But this is endothermic reaction. I'm breaking a bond, a chemical bond. And so the delta H is definitely positive. But I'm making 2 particles from one, so the delta S will also be positive because I'm increasing the translational entropy. And so because of this they're both positive, Kc is going to increase with temperature. And so the equilibrium ratio looks like this. It's the ratio of the R dot to the big R. So how much of these guys, how much at equilibrium, how much of this would be going to the right-hand side is equal to this Kc divided by the concentration of the ethylene. And so above the sealing temperature, where this ratio is equal to 1, then I have more of the little radicals than the big radicals. It means the reaction is running to the right. And so you can compute from the thermo what this temperature is. So at low temperatures, this reaction runs in reverse, and that's polymerization. So a radical adds to a double bond and makes a polymer. Above this temperature, the reaction runs the other way around. The big radicals break up into smaller and smaller pieces and make the alkenes. So it's like you want to run polymerization to make plastic. You take your ethylene, you run it at a low temperature, and the ethylene combines to make polymer. If you heat it up, the polymer will decompose back to the ethylene. So it's very important to know where that temperature is, and then you'll know which way things are going to go. All right, what do the small alkenes do? So you make a lot of ethylene, and in the absence of oxygen, it's gradually converted into acetylene, C2H2. If you have the other alkene you make a lot of is propene. The propene, what it happens is it makes C3H5. It's allo radical, so it loses one H, but then the allo radical is a resonantly stabilized radical, and it stays around for a long time, and then it actually gradually loses hydrogen atoms and becomes an even more stable radical called propargyl, C3H3. And that's another resonantly stabilized radical, and then basically it usually gets stuck there. But propargyl can react with itself, and also different reactions with acetylene can happen, and those reactions all lead to benzene, to aromatic rings. The aromatic ring adds extra stabilization, which gives more, makes reactions exothermic, to do the combination even more exothermic. And so if you're at the ceiling temperature where the alkanes cannot exist, because they want to break up into the alkenes, you could still be at a temperature where the alkenes want to recombine, particularly via acetylene, to form the aromatics. And that would be the thermodynamically stable. And you can see if you run the equilibrium calculation when this will happen. So a key thing is you have to get the oxygen there while you still have ethylene and propylene. If you wait until you make all propargyl and acetylene, you're going to be too late, because then you're going to react and make soot. And then you're going to have a lot of trouble, because you're going to make particulates. The particulates, some of them are going to escape from your flame, and they're going to go and I'm going to breathe them, and I'm going to go sick, and I'm going to sue you because you're giving me emphysema for emitting particulates. So you have to figure out how to try to avoid forming them in the first place as best you can. Secondarily, you can try to trap them and get rid of them afterwards, but it's a lot easier just to not to form them in the first place. So the key there is the mixing of the oxygen. And it turns out the key reaction is this reaction, C2H3. So you have a lot of C2H4. A radical can attack it and make C2H3, steals one H, makes C2H3. This thing is called the vinyl radical. This radical has a really strange reaction where it reacts with oxygen and does a bunch of rearrangements and ends up fragmenting this way into HCO and H2CO. And these guys very rapidly burn up at these temperatures to CO. And so this is the way the oxygen gets into the system. The oxygen reacts with the vinyl radicals and then gets to CO. And that's like the main oxidation. That releases a ton of heat, and that'll keep things going even faster. But if you wait too long, the C2H3 can spit out an H atom by a beta scission reaction to make acetylene, and then you're doomed. You're probably going to make soot. And so you can sort of judge what's happening in the chemistry by how good the mixing is. Is the oxygen getting to the vinyl radicals before they can beta scission? And so it depends on the oxygen concentration, it depends on the temperature. The higher the temperature is, the shorter the lifetime of this guy is, more likely to react unimolecularly than bimolecularly. All right. So what's the difference between different fuels? They all are doing the same thing. They're all breaking up to make a bunch of alkenes. And they're pretty similar, actually. And so the main difference is sort of, do they break up to make mostly ethylene, or do they break up to make mostly propene? Sort of like, do they make odd carbon things with odd number of carbons or even number of carbons? The things that make mostly propylene will have a tendency to make a lot of propargyl, and the propargyl will make benzene, and eventually they'll make soot. So things that make a lot of propylene are actually pretty bad from a combustion point of view for diffusion flames. Yeah, but things that make ethylene are good in diffusion flames because they'll make the vinyl radicals, which react very fast with O2, to break the CC bond and makes carbon monoxide. And so fuels that have a lot of straight chain alkanes tend to break and make a lot of ethylene because those guys continuously do this kind of reaction. Where was it? Here. So I drew this for a 3-carbon chain, but you could have a much longer chain, and it would keep one breaking off and spitting out ethylenes. So things with long alkane chains are good for fuels in diffusion flames. So for example, in jet fuels and diesels, will have a lot of alkane in the fuel, and the long chain alkane breaks up and spits out a lot of ethylene. The ethylene burns up pretty cleanly, so that's a desirable diesel fuel. Things that have a lot of branches would tend to make a lot of resonantly stabilized radicals like propene. Propene that makes allyl and then propargyl, and those will end up making more soot, which won't be as good. There we go. And there's a project going on right now, it's led by Stanford, called the HiChem project, where they're just using this concept to try to understand a whole ton of jet fuels. So people have made 1 million different jet fuels, well, not 1 million, but a lot, 1,000 different jet fuels maybe. And they have different performance, and they make different amounts of soot, for example. And they'd like to understand this. And what they're doing is just experimentally cooking the fuel and seeing how much ethylene, how much propylene, how much methane does it make. And then they have a model for how those small molecules burn in diffusion flames. And so they can predict how much benzene they're going to make, how much it's going to burn cleanly to CO, and so on, by just using the small molecule chemistry detailed model. And they don't need to have the big fuel molecule in the model at all because they just assume it 100% decomposes. And it turns out it matches the experiment pretty well. And then, as I mentioned, this is really important in steam cracking as well. OK, so if you could go and do what the HiChem project is. So a HiChem project is basically doing a ton of experiments where they're cooking a whole lot of fuels and just measuring how much ethylene and how much propylene they make. Another possibility is you could just try to model this. We understand the chemistry. We should be able to make a computer model that does it for us. But we need a lot of rate coefficients because these big molecules can be attacked at many different positions, make many different radicals. They all beta scission differently. And then each of those alkenes you make does some more chemistry and breaks different ways. And so the whole possibility of all the reactions can happen is very large. So we're going to need a lot of rate coefficients. So one idea is just look them up. So hopefully some graduate student before spent a lot of time and measured the rate coefficient that you need. And he's written in a table, and you go to like kinetics.nist.gov, and you can look up the reaction. OK? And so this thing always works for your competitor and never works for you because it's always the molecule that you need is the one that nobody ever measured before. And so there's no number in the database. You could go measure them yourself, do experimental kinetics, and we'll talk about that in a minute. And historically, that was the way that it was done. And definitely, a lot of these reactions are very, it's not that hard to measure them. You can calculate them from first principles, and that's called computational kinetics. And recently, I would say the field's shifting. Historically, it was all experiment. And recently, the computations are kind of getting good enough, and they're faster. So a lot of people are switching over to do the computational kinetics. And those of you who are doing Dr. Klippenstein's course in the afternoon, he's like the expert on that, how to do it. And then we can just estimate them by analogy to known molecules with similar functional groups. And historically, this is how it's been done. So if you guys use models from like Lawrence Livermore, almost all of the parameters are from estimates. If you use models from RMG, most of the parameters are from estimates. So this is probably the way currently, if you get a model, most likely most of the rate coefficients should come this way. Because we just don't have enough experimental ones, and we haven't done enough of the good calculations yet. But we could trust the analogies instead. OK, so let's talk about experiments for a little bit. All right, so if you want to measure a rate coefficient, the main challenge is you have to be able to set up a situation where that reaction is happening on the time scale that you can measure, so pretty fast, but not too fast. Not too fast for your equipment, but pretty fast to get it done with. And the side reactions are negligible. You want to make sure that there's a lot of other reactions that could happen, and you want them not to really compete effectively with your reaction. So that's the main challenge, actually, as an experimentalist, is how can I set up a mixture that's primarily doing the reaction I'm trying to study and not doing other stuff? Because if it's doing a lot of other stuff, it's going to be very confusing to interpret what the results mean. So I want to try to isolate it. So that's a key thing. And then you do that as best you can. And even if you do it, it turns out that it's really hard to do it. And so you think you've isolated and you're going to see just your reaction you care about. But in fact, there's always side reaction 2 and third side reaction, 15th side reaction. There's maybe there's some number of side reactions that are happening fast enough that they actually affect your results. And so you have to consider them as well. And typically, you'll build a model for the other rate coefficients. And then the one that's dominant, you'll maybe try to determine from the experimental data. That's like the main strategy of how to do it. You often have to extrapolate. So your apparatus can measure the rate coefficient at some temperature and some pressure that your equipment can handle. But you might want to use it for a combustion model at an acetylene flame that's 2,600 degrees Kelvin. But you don't have any apparatus that can go up to 2,600 degrees Kelvin. So you're not going to be able to make the measurement at the real condition. Or in an engine, often the pressure is very high. But your apparatus you have in your lab can only go up to 2 bar. Otherwise, your safety guy is going to get really upset if you try to go higher pressure. So you're going to have to do extrapolations. So this extrapolation procedure, typically you have to do it with the help of theory. But even with good theory, you'll pick up some uncertainties. If you try to do it purely experimentally, it's often really problematic to extrapolate very far. All right, so there's a lot of different ways to try to set up the situation that you want. There's a pulse laser photolysis, often called laser flash photolysis. That idea is to make a mixture of the stable molecules at the condition you want, then suddenly irradiate it with light that breaks one of the molecules and makes, say, a free radical, and the radical you want. And so you've suddenly created a whole bunch of radical you want because you've suddenly irradiate with a very short burst of light. And then that gives you like a time zero when the radical suddenly exists. It didn't exist before. And then you're watching the time constant of the decay of that radical. So that's a pretty good method. Another method is flow tubes, where you flow your radical down, say, and your stable molecule down, and mix them up, and flow them down to a detector. And you change the speed at which you flow or the distance at which they flow along, and that sort of corresponds to the time that they have to react with each other. And you see the change in the concentration of the radical at the mixing point and at the later time. Another ones are static studies. So if you have a reaction that's slow enough, you can actually just cook it in a pot. Start up, cook it, stir it up, pull a sample, run it in a GC. So if you have slow reactions, that's a good way to go. For fast reactions, it's not so easy to do. Also, if you have a whole system, you often have a lot of side reactions. If you do this kind of a stir in a pot reaction, a lot of times the reaction is slow enough, things that are relatively minor side channels can actually run long enough that they actually affect the results. And you can get secondary chemistry of your products, so you can have a lot of trouble with these kind of slow reactions. So for the radical plus stable reactions, you want to be able to make the specific radical you want and not other radicals. This is often hard. A lot of systems, things that make radicals, make a ton of different radicals, all mixtures. Like you blast a lot of energy into there, it's going to make a lot of stuff. And it may not just be the one thing you want selectively. Also, can you make enough radicals that you can measure it? So the radicals, it's hard to make them. They're very unstable. They disappear really fast. And so it's hard to make a whole bunch of them. And you have to have a very sensitive detector to be able to detect them before they disappear. They're only like there for a few milliseconds, and they're gone. And you have to be able to look and see them quick before they're gone. And you can't really go to high radical concentrations. If you could figure out a way to make it, it's still no good because the radical plus radical reactions will start to take over if the radical concentration is too high. So you're intrinsically limited that you just can't go above a certain amount. Otherwise, you'll be mostly measuring radical plus radical reactions and not the radical plus stable reaction that you want to measure. Absolute concentration is a huge problem. So for free radicals, you don't have any way to know exactly how many you made. So therefore, you have no way to calibrate what your response of your detector is to the radicals. And so you really want to set up an experiment where you're not sensitive to the you don't need to know the absolute concentration to still figure it out. And usually the experiment measures either the rate coefficient, which is a time dependence, or the final product distribution. Most of the time you can't measure them both simultaneously. The product yields in general require calibrations. And this is a product yields experiments are hard for this reason. So you need to have an absolute calibration for everything you're measuring. So it means you have to be able to make known quantities of each different substance that you want to measure. And also in the product studies, a lot of times the reaction timescales are longer and you see more secondary chemistry. You see the secondary reactions. And so your products you see is a mixture of the primary product you were trying to see plus a bunch of secondary chemistry. And you have to figure out how to deconvolute them. That could be a trick. But for the time constant measurements, you can use this pseudo first order method, which I'm going to show you. And you don't need any absolute calibrations at all. So this technique is super easy by comparison to other options. And so this is actually the most popular thing to do. If you're a kinetics guy, you want to get some papers out quick, make sure you measure a radical plus stable reaction, use the pseudo first order method, and you don't have to calibrate anything. And that's really good. And the key of the idea is that if you have a radical, say X, reacting with a stable molecule Y, your X concentration will be much less than your Y concentration typically because it's hard to make the radicals and you have a lot of stable molecules. So then you can approximate that the ratio of the X at time versus the original amount of X is going to be equal to exponential decay. And the y only appears in here in the exponent. And if y is not, if x is much less than y, then y is not really changing with time, because it's some gigantic number. It's over the whole reaction. It's only changing in the 4th decimal place. So you can basically assume it's a constant. So now you basically have a constant exponential decay. And because you only need the ratio of how much of your radical compared to how much you had initially, you don't need any absolute calibration. So all you have to be able to just measure, have a detection that's proportional to the concentration of the radical, and just measure at 2 different times or 2 different locations. But you just ratio those signals directly, and you don't actually have to try to convert them into the absolute number of radicals. And you still can get the rate coefficient, which is this guy here. But you do need to know absolutely how much y you have. But if y is a stable molecule, that's often not too hard to do. So here we go. So here's one, pulse laser photolysis. Many people do this where they use OH as one of the reactants. OH is a very, very reactive radical, and it's super important for combustion. So it's a great radical to use. And the easiest way to see OH is by laser-induced fluorescence. So OH has an absorption in the ultraviolet. It's a very specific narrow band absorption. You tune your laser directly onto this absorption. Basically, OH has a super strong absorption strength at that wavelength. So if you tune just exactly the right wavelength, you get this really huge amount of the OH excited. And then they fluoresce, and they'll fluoresce at a certain color, very specific to OH. So you can have a monochromator or a filter, so you only detect the fluorescence at that particular wavelength. You can use a time delay. So you excite it to fluoresce, then you wait a little bit, then you see the fluorescence at the later time, and you wait until the laser pulse that made the excitation is all gone, so you don't see any scattered light from your laser. So you have what's called a zero background experiment. If there's no OH there, you won't see anything. And then if you have the OH there, then you'll see a fluorescence coming out at a certain time, at this certain wavelength. And so you know what you're seeing is only due to OH. And it turns out it's sensitive enough, so you can make the measurements. So a lot of people do this experiment. So first you'll make the OH by laser flash of one wavelength, and then say you can start with HONO, H-O-N-O. You can excite that in the 300-something nanometer region. It'll break to make an OH. Then after a little time delay, you flash your laser that excites the OH. After a little bit more time delay, you detect the fluorescence from the OH, and it's a beautiful experiment. So here we go. You set the delay between the photolysis laser and the probe laser, and you repeat it with different delay times, and what you'll measure is something that looks like this. So this is the fluorescence signal as a function of time. Where the time is varying is the time delay between the pump and the probe. So each point here is a different experiment with a different flash, and when I make a long delay, most of the OH is reacted, so it doesn't fluoresce. It's not available to fluoresce. And when I have a short delay, most of the OH hasn't reacted yet, so it does fluoresce. And I can measure the time constant, and this is the time constant of the loss of OH, which is primarily due to the chemistry the OH is reacting. And I can fit this to an exponential, and you can see the fit there. It looks really beautiful. It goes right through all the points. And so you have a pseudo first order decay. Perfect. So this is the very nice experiment. There's probably 300, 500 papers done using exactly this technique. Many people can do it, and it's great. And what you do is you fit these data points to a curve of single exponential decay, and you get an effective K. It's like 1 over tau, the time constant of the decay. And then you you repeat this experiment with different concentrations of your reactant, of the stable molecule reactant. And your K changes with how much of the reactant you have. Because remember our pseudo first order formula? Here. The time constant, the effective K is like K times its concentration of Y. And so if I increase the concentration of Y, I'll make the time faster. The time of the fall will be a shorter time decay. So I run multiple experiments, each with different concentrations of my co-reactant. This is for OH plus SO2. And the time constant gets shorter, which the K gets faster as you increase SO2. And then the slope of this line is the actual rate coefficient that I wanted. Okay, so this is like K prime, which is a product of K times SO2. The slope of this is just K. And then I can do this at many different temperatures and I get an Arrhenius plot, and I'm done. So that's how you do pseudo first order. And I never needed to know exactly how much OH I had. All I needed to know is how much fluorescence I get in my detector. Not even absolute, I just need the relative amount. This is an example of OH reacting with acetylene, the same technique. Very, very popular technique. And you do it for a lot of different temperatures. Sometimes you see goofball things like curved Arrhenius plots. OH is very reactive, so it can do a lot of strange stuff. And the error is primarily to how much acetone we have, actually, in this case. That turns out to, if you do the error analysis, it dominates the error. You can, instead of using fluorescence, another way to detect things is to do mass spectrometry. So you can do the photolysis to make your radicals and then measure the mass spectrum as a function of time. So here's a nice picture of this. If you happen to have a synchrotron available to you, you can do a really beautiful thing where you do the mass spectrum as a function of the ionization energy that you use to ionize it. And if you try to use ionization with a synchrotron where the photon is too low, you'll be below the threshold. You won't be able to ionize it at all, and you won't see the species. And then you increase it, and you'll see a threshold. The threshold position, what wavelength where you see the threshold, identifies the species, because each species has a different ionization potential. And so you just measure these thresholds for the different species, and you can fit them to the photoionization curves and figure out what species you've got. So here's like ethanol and acetaldehyde. Those are the two molecules I showed you before. They're both C2H4O. They both have the same mass, but they have different ionization thresholds. And so with this method, you can get the rate by measuring, you measure the time delay between when you photolyze and when you measure the mass spectrum. That can give you the rate, just like in the flash experiment I showed you before. And you also can get the product ratio by the ratio of how much signal is down here compared to how much signal is up there. It tells you the ratio of the two products. So that's a nice method. This experiment, this actual data set here was the very first observation of ethanol, that molecule. It had never been observed before. So that's why it got published in Science. Because the organic chemists had speculated for a long time it existed, but nobody could ever see it. And this is another variant on the same idea. You can use laser flash to make your radicals in this tube. You let the radicals and products leak out into a vacuum system through a bunch of pinholes. In here, you shine your synchrotron. It ionizes the molecules. You run them through a magnetic sector and onto an array detector, and it gets the whole mass spectrum at a single time point this way. And so here is for this strange molecule, CH2 with two O's in a triangle. That appears in some mechanisms, but I don't think anybody saw it before this experiment. And you can see it, and then you can see the normal isomer of this, which is called formic acid, comes up a little bit later. And then you can vary the concentration of the stable reactant, and you can see the time constant changing, and that's how you get the rate constant that way. This is all for starting with CH2OO. This thing is called the Krieger intermediate. These guys also were the first people to see that one, and they also published in Science because they were the first one to see that one as well. Another one that some organic chemists in 1942 said there should be a species like this, but nobody's ever able to see it before until they had a synchrotron to be able to find it this way. The last one before we'll break. This is a kind of interesting reaction. This is OH radical adding to acetylene to make a hydroxyvinyl. And this is a reaction that's pressure dependent. So if I increase the pressure of like argon in this reactor, I'll measure a different rate coefficient. Pretty weird, huh? So what's happening is that when the OH reacts with the C2H2, it can make this molecule, has like maybe a low barrier here. So there's a low barrier for these guys to react. They react across this little barrier, and they form HOCH, something like that. It's a hydroxyvinyl. But this guy it's a very exothermic reaction because OH is a very hot radical. This is a triple bond. Triple bonds aren't that stable. So it really wants to react to make this a lot more stable. But that means that when you form it in the vacuum, you form something with this much energy because energy is conserved when these bonds come together. So you're forming this guy, but it's at an energy way above the bottom of the valley. So this is like very vibrationally excited, this molecule. And what this molecule can do is this excited one is above the barrier, so it can just go right back. And in fact, that's mostly what it does. So the OH doesn't want to react with acetylene. It wants to react. It reacts. But then it has too much energy, and this guy falls back apart because it's already above the dissociation limit. However, if I have an argon molecule here, and the argon bumps into this guy, the argon can take away some of the energy and lower this down to some little lower energy, which is trapped into the valley. And now I make the product. And the more argon I have, the more this will compete with the back reaction. And so when I measure the rate for this guy, the rate law is K times concentration of OH times concentration of C2H2 times the concentration of argon. The more, and I see it like that. And this guy is not actually doing any reaction. All he's doing is just carrying away energy. And so this is a major reason for the pressure dependence you see in combustion chemistry. So why high pressure combustion is really a lot different than low pressure combustion is there's a lot of reactions like this where you're limited by how fast you can take away the energy, not by how fast the reaction can happen. The reaction happens really fast, but your thermal dissipation in the gas phase is too slow to keep up with the reaction. And so you're actually rate limited by this, not by going over this little tiny barrier because the OH is so reactive. All right. See you guys at lunch.